A magnet is a material that generates an invisible magnetic field around itself. Two powerful neodymium magnets can snap together with enough force to crush objects caught between them. Without magnets, many of the technologies that power our modern world simply wouldn't exist. From electric motors and high-performance speakers, to computer hard drives, contactless payment systems, MRI scanners, smartphones, household appliances, renewable energy systems, and even satellites. Magnets work silently behind the scenes every day. But how are the world's strongest neodymium magnets actually made? Join Chronicle Travels as we go inside the factories where rare earth metals are transformed into one of the most powerful materials ever engineered. A magnet is a material capable of generating a magnetic field around itself. This invisible field allows it to attract or repel certain metals, particularly ferromagnetic materials such as iron, nickel, and cobalt. Although magnetic fields cannot be seen with the naked eye, their effects are present in countless technologies we use every day. Not all magnets are created the same. They are generally classified according to how they are formed and how they produce magnetism. The first category is the natural magnet. The best-known example is magnetite, a naturally occurring mineral that possesses magnetic properties without any human processing. These naturally magnetized rocks were the earliest magnets ever discovered and helped scientists understand the phenomenon of magnetism centuries ago. The second category includes permanent artificial magnets. Unlike natural magnets, these are manufactured from specially selected metallic materials. A third category is the electromagnet. Unlike permanent magnets, electromagnets only produce a magnetic field, while electric current flows through a coil wrapped around a metal core, usually iron. One major breakthrough arrived during the early 20th century, with the development of alnico magnets, produced from aluminum, nickel, cobalt, and small amounts of other metals such as copper, iron, and titanium. Alnico magnets offered much stronger magnetic performance than earlier materials, and quickly became popular in industrial applications. Later came ferrite magnets. These were less expensive to manufacture, highly resistant to corrosion, and suitable for mass production. Although they weren't as powerful as alnico magnets, their affordability made them the preferred choice for loudspeakers, household appliances, electric motors, and countless consumer products. Everything changed during the 1980s, when researchers introduced an entirely new class of permanent magnets based on a rare earth element called neodymium. Neodymium itself was first identified in 1885 by Austrian chemist Karl Auer von Welsbach. Nearly a century later, scientists discovered that combining neodymium with iron and boron created an entirely new magnetic material, capable of producing magnetic forces far beyond anything previously achieved. The result was the neodymium iron-boron magnet, commonly known as the NdFeB magnet. These magnets are dramatically stronger than traditional ferrite or alnico magnets, while remaining much smaller and lighter. Today, neodymium magnets are considered the most powerful commercially produced permanent magnets in the world. But creating such remarkable magnets doesn't begin inside a factory. Their story starts millions of years earlier, hidden deep underground inside rare earth mineral deposits, where enormous mining operations extract the raw materials that make this incredible technology possible. Although they are called rare earth elements, most of them are not actually rare. Many exist in relatively large quantities within the Earth's crust. The real challenge is that they are widely dispersed and tightly mixed with other minerals, making them extremely difficult and expensive to separate. Neodymium belongs to a family of 17 rare earth elements, and it is usually found alongside many of the others, rather than in pure form. The two most important minerals containing neodymium are bastnasite and monazite. Large bastnasite deposits are found mainly in China and the United States, while monazite is mined in countries such as Brazil, India, and several other regions around the world. The journey begins at massive open-pit mines. Before any ore can be removed, engineers carefully survey the deposit and identify the richest sections of the rock. Powerful drilling machines then bore deep holes into the ground. following carefully designed blast patterns. Once drilling is complete, controlled amounts of explosives are placed inside the holes. When detonated, the explosion breaks enormous sections of solid rock into manageable fragments, without damaging the surrounding mining area. After blasting, giant hydraulic excavators and wheel loaders collect the broken ore and load it into heavy-duty mining trucks. These massive vehicles transport hundreds of tons of material from the mine to nearby processing facilities, where the real separation process begins. Large industrial crushers break the ore into smaller pieces. The crushed material then passes through grinding mills, where it is reduced into a fine powder. Next comes one of the most important stages of the entire operation: chemical leaching. The finely ground ore is mixed with carefully controlled acidic solutions, commonly containing sulfuric acid. During this process, the rare earth oxides dissolve into the liquid, producing a solution rich in dissolved rare earth ions, including neodymium. After numerous cycles, neodymium is finally separated from the remaining rare earth elements. To recover it as a solid material, technicians add a chemical base, commonly ammonium hydroxide. This reaction converts the dissolved neodymium into an insoluble compound known as neodymium hydroxide. It is then dried under carefully controlled conditions to eliminate remaining moisture. It is transferred into high-temperature furnaces, where intense heat converts it into neodymium oxide, a stable gray powder that serves as the primary raw material for manufacturing high-performance neodymium magnets. The neodymium oxide is sealed inside heavy-duty steel drums for safe storage and transportation. These containers are then shipped to specialized manufacturing facilities. With the purified neodymium oxide arriving at the manufacturing facility, the first step is to prepare the metallic alloy that gives neodymium magnets their extraordinary strength. Instead of using pure neodymium alone, manufacturers combine it with iron and boron to create what is known as the NdFeB alloy. The raw materials are carefully measured before being loaded into a vacuum induction furnace. Inside the furnace, oxygen is removed to create a controlled atmosphere. This is especially important because neodymium reacts very easily with air at high temperatures. As the temperature rises above 1,300 degrees Celsius, the metals gradually melt into a single liquid alloy. Powerful induction heating keeps the molten metal continuously mixed. Once the alloy reaches the required composition, it is ready for casting. Before the molten metal can be poured, specialized molds must be prepared. A solid pattern of the desired shape is first placed inside a molding box. Special molding sand mixed with binding agents is packed tightly around the pattern. In many foundries, a curing gas is then injected into the mold, and creating a strong, highly detailed mold without the need for heating. After the pattern is removed, a perfectly shaped cavity remains inside the mold, ready to receive the molten alloy. The glowing liquid NdFeB alloy is then carefully poured into these molds. As the molten alloy enters the mold, the intense heat often ignites the binding gases within the sand, producing brief flames around the casting area. Although dramatic to watch, this is a normal part of the process in many foundries. After pouring, the alloy begins to cool and solidify. The cooling process is carefully controlled. Cooling too quickly may introduce internal stresses or cracks. Once the metal has completely solidified, the sand mold is broken apart, revealing the newly formed casting. At this stage, it still possesses no permanent magnetic properties. The cast components are carefully arranged inside heat-resistant metal tubes and surrounded with fine silica sand. After the tubes are sealed to prevent oxygen from entering, they are placed inside industrial furnaces for controlled thermal processing. When the heat treatment is complete, the alloy has reached its optimal internal structure. Now, it is finally ready for the most remarkable step of the entire manufacturing process: the moment when an ordinary piece of metal is transformed into a permanent magnet through the power of an extremely intense magnetic field. The final transformation happens during a process known as magnetization. The finished alloy is placed inside the magnetizing fixture, and the high-energy pulse instantly forces nearly all of its magnetic domains to align in the same direction. Within a fraction of a second, the transformation is complete. What was once an ordinary metal alloy has now become a permanent neodymium magnet, capable of producing an incredibly powerful magnetic field. Because of its unique crystal structure, the aligned magnetic domains remain locked in position, allowing the magnet to retain its strength for many years. Their magnetic force is strong enough to pull nearby metal objects together with tremendous speed. If two large neodymium magnets collide unexpectedly, they can chip, crack, or even shatter due to the enormous impact force. Neodymium magnets will remain one of the key materials driving technological innovation around the world. What appears to be a simple silver magnet is actually the result of millions of years of geological formation, combined with decades of scientific research and some of the most advanced manufacturing techniques ever developed. If you enjoyed this video, don't forget to like, subscribe, and leave a comment. Thanks for watching, and we'll see you in the next journey.